Good. Well, hi. Thanks for the intro and for having me, Peter. As you said, the talk is titled "A Gentle Introduction to Conformal Prediction and Distribution-Free Uncertainty Quantification." The basic idea of this set of techniques is that they allow you to produce rigorous finite sample confidence intervals. In this case, they're actually called prediction intervals that work for any model and any data set and also don't cost you anything. So it's just a really cheap computational procedure that you can run on top of any pre-trained neural network, and it will stamp it with the certification that it satisfies some statistical guarantee. For example, that you contain the correct answer inside some prediction set with high probability. Analogously with confidence intervals and when you work in biology or something. So just to reiterate, what we're going to do is we're going to take some pre-trained net that you guys have, some ResNet or whatever. And instead of just making it output a point prediction, for example, a class, it's going to output a set of point predictions, a prediction set, like, the set dog, cat, squirrel, and so on. And this thing will have a guarantee. And the guarantee will hold no matter what your data set, no matter what your model is, no matter what level you set your guarantee to. And it doesn't cost you much compute. So as you can see, these are black box techniques. They require no special analysis, no matter what underlying base technique or what underlying prediction problem you're using. And the presentation is going to be a tutorial. So you guys by the end should understand how to implement this. And we're going to start with image classifiers since everybody here likes vision. All right. So let's talk a bit about motivation. Well, why do we care about having prediction intervals with statistical guarantees? It's because we're going to be using our computer vision models for downstream decision-making tasks. And in those tasks, accuracy might not be enough. So for example, let's say I'm a doctor and I get an MR image of somebody's brain along with the putative diagnosis of some ResNet. So the ResNet sees the image and says, oh, this person's normal, send them home. I think all of us that work with computer vision algorithms know, well, you can't really trust the model 100%. Even if it's 90%, 95% accurate, the person might fall in the 5%. You really wouldn't know. And these errors can be unpredictable. They can fail, models can fail in unknown and even unknowable ways. So what you really need is something that will allow you to rule in or rule out different diagnoses per patient, right? So as a doctor, you need to be able to say, well, with 99% probability, this person's either normal or they have a concussion or they have cancer. And then with that 99%, I can then make my decision. Well, if it's 99% one of these three, and these two are pretty severe, then maybe I need to do further tests. But if the set just contains normal, then maybe I do send the patient home. So this is the type of guarantee that we're going to be able to get. In fact, we're going to be able to get exactly this guarantee below. That the true diagnosis lies in the prediction set with 90% probability or 99% probability or whatever probability you choose. Okay, so that's the motivation. Maybe before we get into some technical details, do people want to ask questions about motivation, or is this clear? Perfectly clear? Good. So let's start with classification. So I'm just going to lay out some mathematical notation here so that we can follow along. The goal in classification is that we're given three things. We're given a calibration data set. This is fresh data that the model hasn't seen. And it contains tuples of images, which are our x's, images and classes. The classes are our y's. And the classes live in some discrete set, 1 through k. So you can think about this as ImageNet. If it were ImageNet, it'd be 1,000 classes, 1 through 1,000. And each of these would be one of the ImageNet classes. And we have n of these calibration data points. We don't know, and this doesn't hold for some specific n greater than some number. It's just we have n of them, for some integer n. And all of these examples are sampled from some probability distribution IID with no assumption on what this probability distribution is. The second thing we're given is a model. The model is called pi hat y of x. The model estimates this conditional probability distribution, which is the probability of any label given the image. Okay, so it's estimating this, but we don't know it. We wish we knew this, we don't. And this might be arbitrarily bad. So this is just your classifier. This is your neural network. And then we get a new image, x sub n plus 1. That's not in our calibration set. We've never seen it before. And we're asking you to predict a set. Okay, the set is going to be called t of x n plus 1. The set is a subset of your label space. So this is a set of, 1, 10, 90, or whatever. It's a subset of this. And we want to give you a guarantee about the set, okay? So this function here, t, is a set valued function. It takes in your new image and it outputs a set. And we want that to satisfy the following guarantee, that it contains the true class with high probability. So that's what I've written below. This is called coverage. So I'm going to zoom in on it, and we're going to parse it really quickly because it's our main quantity of interest, at least for the first half of the presentation. Okay, so what is coverage? Coverage says, oh, why is my pen not working? That's no good. Well, we'll see if that works later. But for now, I don't have any more red pen. So just starting from the left on the equation, this probability symbol, I'm saying the probability y sub n plus 1, which is your new label here, there we go. New label is in the set generated when you plug x sub n plus 1 into your function, is greater than or equal to 1 minus alpha. Okay, so that's called coverage if you have this property. This is saying true diagnosis is in set of diagnoses with high probability. So let's try to get a sense for what this function t is. So this is our t of x, these three things here, these ones. So what happens is what I've done here is I've plotted 3 squirrels from ImageNet. This is an easy squirrel, medium squirrel, hard squirrel. Okay, so they go increase in difficulty from left to right. Why is this an easy squirrel? It's because its background makes sense. The squirrel's in full view, and the model has seen a lot of squirrels like this, so it's pretty confident. And so because it's confident, it outputs a prediction set that's of size 1. Okay, so this thing is of size 1. Cardinality is 1. Cardinality t of x is 1. Okay, so the model's confident, so it gives you a small set. But now if you look all the way on the right-hand side, this squirrel doesn't even look like a squirrel. Its head's cut off. Its background doesn't suggest that it's a squirrel. It's got this flat, weird tail. It might not even be a squirrel, actually. I kind of do think it looks like a marmot. And so does the ResNet, as you can see here. And because we're unsure about this squirrel, we get a large set. Okay. So just to summarize what we want from these sets, what we really want from the sets is, first of all, we want them to have exact coverage, right? We want them to satisfy this guarantee that we talked about above. Otherwise, there's no point in doing any of this, right? It's going to rigorously satisfy this guarantee, period. But then we also want some other things. We want them to be generally small. Smaller is better because it's more useful for decision making. And maybe more importantly, we want them to be adaptive. We want them to be smaller for easy examples and bigger for hard examples. In other words, we want the size of the set to give us a signal about the difficulty of the example. Okay? By the way, there's an easy way to get exact coverage trivially, which is, I guess you can tell me what it is, right?
All the options.
Yeah, just always give me the entire space script y. Yeah, so you can always give me coverage. What we really like, coverage is meaningless without having these two things. By the way, you can always give me exact coverage as well, which means that you give me this, but with an equal sign, which is better. And you can do that with a randomized version of what you just said, which is this. You give me the whole space with probability 1 minus alpha, and you give me the null set with probability alpha. Okay, so this would be stupid. And what we want is something that looks more like this. And in fact, we're going to get it. The quality of t of x depends on the quality of your model. So that's where the machine learning comes in. Okay. So now we're going to talk about how do we produce these sets. How do we produce these sets? And the way that we do it is basically we use this, you remember this calibration data set that we had held out at the beginning. We're going to use this calibration set to learn a rule to predict sets. And it's not going to be gradient descent learning. It's just going to be the simplest algorithm you've ever seen. You know, this is basically a two-step algorithm. It's going to give you exactly the guarantee that we described above. So I'll just, we're just going to learn the entire algorithm right now. So I'm just going to zoom in step by step. The first step of the algorithm is you get the score of the correct class on each example in your calibration data set. Okay, so what does that mean? That means I take my neural network, I calculate neural network of X sub I. Now I have a vector of softmax scores, right? That's this. And then I look at Y sub I, which is the true class corresponding to the image X sub I. And it has some score, right? The model gave it some softmax score. So I'm just going to draw this here. This level here of that softmax score, we're going to call E sub I. Okay. Now we do this for each of our xi, yi pairs. So we now have a sequence of these, I equals 1 through n. Right, we have one for each calibration point. We just loop through and do this procedure. Actually, you can vectorize it. Okay, so that's step one. Step two is you take roughly the 10% quantile of these things. So there's a little finite sample correction that I'll explain in a moment. It's not exactly 10%, but it's really close to 10% when you have n larger than 100. So what you do is you take roughly the 10% quantile and you just store it as this variable q hat. So just to be clear, I'm going to draw out what this means. What this means is I make a histogram of all of my E sub i's, all of the scores for the true classes. And then I look at this level here, q hat. Q hat is a level such that 10% of the mass is below and 90% of the mass is above, roughly. Okay, so what's the interpretation of q hat? Q hat is a threshold. Q hat is a threshold such that at least 90% of the examples that I've seen have a score above q hat. Okay, so that's the key idea. Now, after we've done this, our calibration procedure is over and we can deploy. So I'll show you what it means to deploy. Deploying is forming prediction sets. So you give me a new x sub n plus 1, and I form the following set. This is our t of x. And I'm going to call it tq hat of x sub n plus 1, sorry, equals this thing. It's the set of all classes whose score exceeds q hat when x sub n plus 1 is input. Okay? So I'm actually just going to draw what that means. I take my neural network, I put in x sub n plus 1. I get a vector of softmax probabilities. I threshold them at q hat. And these 4 people go in my prediction set. So what is the prediction set? In this case, it's 2, 3, 4, 5, 6, 7. Okay. So this prediction set here has the following guarantee. Not only do you have coverage, so this is the guarantee that we've been talking about before. Not only do you get coverage, the true label is in the set, but also you have this upper bound that says my coverage is also not too conservative. So just plugging in numbers here, if n equals 100, in other words, if you save me 100 calibration points to do this procedure, this conformal prediction procedure, then I set alpha equal 0.1, which means I want 90% coverage. I'm going to get between 90% and 91% coverage. roughly. Okay, so I'm not going to be too conservative. And this guarantee, this theorem, holds for any algorithm, any data set, any level alpha, and any n.
Could you explain, I don't know if you're going to get into this, but like why this is true? Just picking this Q hat in this way gives you this property, or what assumptions go into this to make it?
Yeah. Yeah, I can go into that, but let me give you an intuitive understanding of it since you asked the question. The intuitive understanding is, so what is the assumption in this theorem? Assumption is just that the E sub i's, I equals 1 through n plus 1, are exchangeable. You should think of this as IID. IID is sufficient for this. Okay, so what that means is, another sufficient condition for this is that all of the calibration data comes from the same distribution as my new test point. So distribution shift is not handled by this procedure, although there are variants of conformal prediction that can handle distribution shift in certain settings. Now, by the way, these procedures are very new, the ones that can handle distribution shift. Now, I guess the other question would be, like, intuitively, why would we expect picking Q hat this way to yield this guarantee? So let's just think about it for a second. This has to do with step 2. So you remember, I told you Q hat is this quantile. It's roughly the point where 10% of the mass of the E sub i's lands below and 90% of the mass lands above. Okay, so let's think about what would happen if n were infinity. If n were infinity, what property would Q hat satisfy? Can you think about it? Can you tell me something?
Normal distribution
Well,
around the medium and some standard deviation for IID.
actually, there would be, I don't think there's a normal distribution here. The score distribution is unknown in advance. So for example, you might have that your model gives you scores that look like this. It's sort of like they're almost all near 95% because your model is usually pretty confident on the data that it's trained on. So it's not going to be normal. In fact, it usually looks like a beta distribution, beta like 2.8. This is my favorite little fact, is that I think ResNets all follow this distribution. But it's not actually a fact. Don't write it down anymore. But no, so it's a property of Q hat that we're looking for. Sachin or Jeff, do you want to take a guess?
I'll wait for the real answer.
Okay. So the real answer is this. When n goes to infinity, Q hat is the true quantile. Q hat is exactly the point where there's probability, a new point, X test, or like E test, is below Q hat is equal to 10%. So this will be true as n goes to infinity. So what happens if the probability E test is less than Q hat? Do you understand why this is true, by the way, as n goes to infinity?
No, please explain.
Yeah, that makes sense.
So as n goes to infinity, this histogram of scores that we made here is going to converge to the true distribution of scores. It's going to be the actual thing.
But unless I'm missing something, This distribution of scores is each time per sample or per I. Or I missed something in before.
Yeah, it's not per I. So the way that you form this is you take all of your E sub i's. So you have n calibration points. And then for each of those calibration points, you calculate the score of the true class. And you label that E sub I. Now you have n calibration points. This is the sequence of E sub i's equals I equals 1 through n. And now what happens is that this histogram, the axis labels on this histogram are, let me put this up here, Q hat, are E sub I and like number or frequency. Yeah. So this is like now becomes the true distribution of the E sub i's. And this is a quantile of the E sub i's. So that's why this thing will eventually become exact. As n goes to infinity, this histogram will be perfect. Okay. So what does this imply? If we know that the probability, the score of a new example is less than Q hat is equal to 10%, then what happens? If I take, what this says is, what is E test? We take NN of X test, and we, let me just write it in our language so that I have a formalization for it, but we take pi hat of Y test of X test. This thing is E sub I. It's the score at Y test when we put X test in our model. The probability that this thing lands below Q hat is 10%. So the probability this guy lands below Q hat on this histogram is 10%. Right? That's exactly what that means. Now let's look at how we formed the prediction set. The way we formed the prediction set is we took a new test point, X test, same thing as xn plus 1. We plugged it into our model and we looked at the scores of all the classes. Now what this gives us is that the score of the true class lies below this line with no more than 10% probability. So if we threshold here, there's 90% probability that the true class lands in here, in this set. And that's what the guarantee says.
Got it.
Does that answer your question?
Yeah, for sure. I think there's just some confusion in going from, in step 2, we're considering this distribution over the correct EIs. So like what the actual like score for the correct class is, we have some distribution over that.
Exactly, yeah.
Versus in the third one, now we're not considering just the correct ones, we're considering the scores for every class.
Yeah, and you don't know the true label in 3. That's right. But the fact that you know that it lands below this line with no more than 10% probability is the thing that gives you the guarantee. Okay. So by the way, this strategy, which is called conformal prediction, was pioneered by this guy Vladimir Vovk and his collaborators in Royal Holloway University. Vovk is also Ukrainian. I talk a little bit about the history of conformal prediction in my gentle intro, so you guys can read that section. Okay.
Quick follow-up before we go to the next step while we're just still on this. So you said the assumption, so it seems like basically what we're doing is we're saying, okay, we have some distribution over EIs that we can get on the calibration set, and we're going to assume since they're IID or like exchangeable, then it forms like a proper distribution that we can take a quantile of and say that that matches the true thing. But is that assumption basically saying your confidence is not correlated across training samples? Like you're not consistently overconfident on certain types of inputs?
So it's not assuming that. It's just that you may be consistently overconfident on those inputs, on like some fraction of like X. You know, if X is some space, you know, this is X, script X, all of your X's are drawn from here. And it may be that, you know, in this slice of X, your model's always overconfident. But those overconfident scores are going to show up in the histogram. Right? They're going to show up because they'll push the score of the true class down. Right? So then more mass will end up down there. If this is this doesn't mean that, so what we're not giving you is something called conditional coverage. What we're not telling you is that no matter what X you pick, you get this guarantee. I'm not saying conditionally on X sub n plus 1, this thing holds. It's just on average over all of the training data. So you may be systematically making your errors all on this slice if that's where your model's overconfident. But as long as on average over everything, I'm giving you 90% coverage, that's okay from the perspective of at least this version of Conformal. But you're bringing up something interesting, which is that there's better ways of doing this that try to make coverage equalized over all parts of your space. And that's what the this adaptiveness criterion is about. So if you want to read about that for image classification, I have this paper, Uncertainty Sets for Image Classifiers Using Conformal Prediction, which I think I may have actually linked already. And that talks a lot about adaptiveness. And we rely also on this procedure, the APS procedure, as we've named it in the paper, that Yaniv Romano and Emmanuel Candes came up with. And we modify that to get better adaptiveness.
Cool. Later or at some point, you're going to be able to talk about how this applies to regression analysis as well, specifically maybe even time series.
Yeah, absolutely. So time series is a tough one because time series, there's distribution shift. There's ways to do conformal for time series. They're a little advanced. The version that I like best for time series was published a month ago. And so I can explain it to you. Maybe I'll explain it at the end. I'll have to like sort of ad lib it. But yeah, so why don't I move on to regression? So there's two options here. One option is that I can sort of explain to you a better way of doing classification. So this isn't actually the way that I suggest, the way that I showed you. There's a slight modification that's an improvement. But you guys can also just read the gentle intro for that. The other thing is that I can explain to you how it works for regression. And then there's like this whole second half to the talk where I talk about how you can do this for very complicated problems like image segmentation, object detection, instance segmentation, and so on. So do you guys have a preference as to what we do? We're not going to have time for all of it. So I think at least one of these things is going to have to be cut.
I think let's do the other two. Yeah, like the regression and the image segmentation.
Okay, sounds good.
Yeah, I agree with that.
Great.
Same.
That's what we'll do. Okay, so just before moving into these, let's just zoom out and think about what we did with Conformal. We took some heuristic notion of uncertainty that our model gave us. The heuristic notion of uncertainty was 1 minus the softmax score of the true class. Right? Why is this a heuristic notion of uncertainty? It's because when 1 minus the softmax score of the true class is small, that means our model is really certain. And when it's large, it means our model is really certain, really uncertain. Right? So big 1 minus means my model doesn't know what's going on because it's giving the true class a small score. And we ran it through this machine that we call conformal prediction, and out we got a rigorous notion of uncertainty. Out we got this probabilistic guarantee with this theorem. And it held no matter what, basically, as long as our data was IID. Now, the heuristic notion of uncertainty doesn't need to be 1 minus the softmax score of the true class. It can actually be any number. It can be any number. And that's the magic of conformal. Then the question becomes, how do I design a good number? How do I design a good heuristic notion of uncertainty that's going to give me the behavior that I seek, which is this adaptiveness, right? So, continue with our zoomed out general case of conformal prediction. After we identify this heuristic notion of uncertainty, so keep this 1 minus softmax score in your head, you define a score function, okay? The score function is the E sub I from before. The score of the true class, 1 minus. And then we compute this quantile. So, by the way, I'm carrying around a 1 minus with me because it's convenient. But before we did the 10% quantile, now we're switching into the 90% quantile because of this 1 minus. Okay, so you take roughly the 1 minus alpha quantile. Right, and I have this little correction, n plus 1 over n. And the n plus 1 over n, with the seal, it deals with the fact that n is not infinite, and so we didn't estimate the quantile perfectly, okay, when we were making that histogram. And then after we've estimated q hat, then we deploy. So we deploy the set of y such that the score is small, which means that our model is more certain on these points. Okay, so if you just plug in what we had from before, our score from before was 1 minus E sub I is less than or equal to the 90% quantile. Right, that's the same as being E sub I is greater than the 10% quantile. And this holds no matter what score function you choose. Deploying this TQ of X will give you the guarantee. Okay? And the reason why is because of what we said before. It's because of this IID-ness thing. The idea is if that you like plotted all of your scores on the real line, the probability you'd land in any gap between the scores is equal. And so that's sort of the fact that we're using. Okay, so that's where the exchangeability comes in. And then you'll get this coverage guarantee. Okay. So now how do you do this for regression? So the way that you do this for regression is that the first thing you do is you try to estimate the conditional quantiles of y given x. So you do something like add a pinball loss to the end of your model. And the pinball loss of your model says, okay, well, there's some relationship between y and x. Let's imagine y and x are both one-dimensional. And we're just trying to do regression. We're trying to regress, I don't know, income level to lifespan or something. And there's some like sort of true mean here. There's some true conditional mean. This would be like expectation of y given x. But the mean is a function of x. But also there's some width to it, right? This is sort of a quantity that has intrinsic variability. And so we also need to estimate the quantiles. So this would be the alpha quantile, and this would be the 1 minus alpha quantile, like that. Okay, so we're estimating these via quantile regression, which you guys probably have heard of, quantile regression, but let me know if you haven't. And then what we do is we look at how bad our quantile regression algorithm is. And we call that our score function. Okay, so in other words, we plug in x sub I from our calibration data set. We calculate, and then we look at y sub I. Y sub I is some continuous value, right? So it lands somewhere along here. Let's say it lands here. Then we look at this distance here. It's like the projection from y sub I onto the closest quantile. And that becomes our score. Right? And then what I do is I take the quantile of these guys and I just add it to my quantile regression. So I'll inflate my quantile regression or deflate it, depending on the direction of the sign, by the quantile of SXIYI. Okay, is this making sense? Okay. By the way, quantile regression was pioneered by Conker and Bassett. I think that's how you spell it. And what was it, 79? I don't remember when this paper was from. In Econometrica. But it's just crazy that quantile regression is so recent. You'd think that Gauss invented quantile regression, but no, Roger did. So yeah, this is the regression idea. If anybody has any questions, I'll take them now. Otherwise, we'll move on.
On my end, no. I think the idea is clear.
Right.
I have one question also related to the previous topic. Like, how does, so you said like any score works, and we were just talking about 1 minus softmax. How does this relate to the strength of your model? Like, if you have a model that gives better predictions, then what is the relationship between that and these things? Like in our previous theorem, would that mean you need to toss less things in the set to get it to be above the threshold? Or yeah, I was just wondering if there's more detail.
Yeah, great question. Great question. Great question. So the answers to your question is basically yes, that you have it right. So let's think about what would happen. If I have a score function, like if I go up here, if I have a score function that's just random noise. Okay, so I'll define a score function for you here, a really terrible one. Okay, so each one of these, each score is like an independently randomly sampled normal that has nothing to do with your data at all. Then what do? I calculate Q hat. Q hat will be the quantile of the normal distribution. So, you know, your normal distribution will look like this. And the quantile will be here. That'll be Q hat. And then what will happen at prediction time? What will happen at prediction time? At prediction time, for every y, I'm going to sample a normal, because that's what my score does. And then I'm going to look at how many of those normals fall below Q hat. Now I chose Q hat as the 90% quantile of the normal. So 90% of the y's, a random fraction of my label space, 90% of it is going to land in this set. And so I'm going to get coverage of 90% because I randomly selected 90% of my labels. Okay, but my T of X is going to be huge. The cardinality is basically always going to be 90% of my 90% cardinality Y. And also it's not going to be adaptive at all. It's literally just going to be a random subset of my labels. So that's what happens if I have a bad score. If I have a good score, I get the behavior like this one above. That like the score function is big when my model is uncertain and small when my model is certain. So I get smaller sets that are adaptive to difficulty. I don't need to take the entire label space all the time. Does that answer your question?
Yeah, pretty much. Cool.
Great.
Thanks.
No worries. Okay, so part two of the talk is more complicated problems that are not one-dimensional. And for that, you need techniques that are more advanced than conformal. So I'll explain some of those. So what do I mean by beyond simple problems, beyond one-dimensional problems? I mean problems like the ones that we do in computer vision, like tumor segmentation or instant segmentation, object detection, and so on. There might be multiple notions of risk that we care about, or the relevant notion of risk might not be coverage. Right? We might want a segmentation mask that contains 90% of the tumor with high probability. Or we might want control over recall, IOU, and coverage. because in detection, we're doing 3 tasks at once. We're trying to identify all the objects in the image. We're trying to segment them all, and we're trying to give them a class. So there may be a multifactorial notion of error. Okay, so these are the types of things that we'll be able to address with the next framework. So let me just give you an intuitive example of how this works. It's kind of like a generalization of conformal. And in fact, in certain settings, it's an exact generalization of conformal. So let's say I'm doing segmentation. So I have a tumor segmentation problem laid out here. And my x's are like images of tumors. That's, m by n. My y's are binary. And then I have this model pi hat sub y of x, which gives me, for each pixel, I get the probability that it comes from a tumor. So it's the output of a sigmoid layer at the end.
Where is the notation of the pixel in that pi y of x?
Oh yeah, well, I guess this is the wrong notation. Let me call it this. F hat x I comma j is equal to probability pixel, estimated probability pixel I j comes from tumor. Is this better? Good. So that's what we'll call F hat. So what we're going to do is we're going to threshold those probabilities at some level. So by the way, I'm going to put a hat over this. This is our F hat. So just imagine that we're looking at a slice of tissue here, like this guy. Well, this is just, this is the tissue axis. This is the region in the image. And this is the model's estimated probability that it comes from a tumor. All we're going to do is we're going to take super level sets of that. So things that our model thinks are sufficiently likely to be from a tumor are going to be considered part of prediction sets. So what happens, so we have this parameter lambda. Parameter lambda is going to be indexing our set. The set in this case is just going to be a set of pixels. If lambda is very large, if lambda equals 1, we take nothing in our prediction set. And if lambda is very small, like down here, then we'll take everything. And what we'd like to do is pick a sweet spot here. We'd like to pick the largest lambda, i.e. the smallest set that contains 90% of our tumor. Okay. And this region here, this is going to be like our T sub lambda of x, where lambda is a free parameter that we choose. So this will be like our set value function from before.
So now my bells are dinging and saying, but this is not IID, the pixels here.
Pixels are not IID, so we're going to get a guarantee over the entire image.
Mm. Okay.
The pixels, by the way, would be sort of exchangeable if you shuffled them, but that would not be the right thing to do. The right thing to do is to sort of shuffle all the examples, all of the images together, not to shuffle the pixels.
Yeah. Then this would be, yeah.
Exactly. So that's what we're going to do. We're going to get a guarantee over the image that 90% of the tumor is contained.
Mm-hmm.
And that's part of the reason why you need these new techniques, is because this doesn't really even make sense when you talk about pixel level stuff. Okay. By the way, we're going to control a risk function that's not coverage. The risk function in this case is 1 minus the number of shared pixels between the fraction of tumor pixels contained in my set. It's the cardinality of y intersect t lambda x. So this is the fraction of pixels in the tumor that are contained in my set, right? We take the expected value of 1 minus that. That's like a loss. This is called a false negative rate, this quantity. 1 minus the fraction of good things that I contain. Okay, so that'll be our risk function. Actually, we'll be able to control any risk function. Any expected loss can be controlled by the same set of techniques. This is just one that we're going to be controlling. Just think about what this means, the false negative rate. As lambda shrinks, i.e. as our sets get bigger and bigger, they'll contain more and more of the tumor, and so our false negative rate is going to go down. The more pixels we contain, the smaller our false negative rate is. Okay? So what we want to choose is the largest lambda, i.e. the least conservative set, such that we're not highlighting all the pixels in the image, such that we contain the tumor. All right? So let's draw this graphically. And I'm going to draw it for a general risk. So we have a risk function here. The risk function takes in, or it's the expected value of a loss function, which takes in the prediction set and y, where y is the binary mask, and t lambda x is also a binary mask indexed by lambda. And I just plotted it on here, okay, as a function of lambda. So as lambda changes, our risk changes, right? Because our set is changing. And I plotted it here, and I've also plotted a desired risk level alpha. So let's say you don't want your, you don't want more than 10% of the tumor to be missed. That would be your notion of confidence. You know, if you pick alpha equals 0.1, you say, I want 90% of my tumor to be contained in the set. Now the sub-level set of alpha, of the true risk, is the thing that we want. We want all settings of the threshold. All settings of the threshold such that our risk is controlled. Okay, so we're going to try to estimate that. We're not going to be able to get this exactly, but we're going to be able to get a subset of it. And then oftentimes we're going to pick an extreme point, such as the largest lambda that controls the risk. Okay, so we're interested in this point here, oftentimes, or this point, depending on the direction of the risk. Okay? So if I pick any lambda that lies here, in this blue part, i.e. any lambda such that the risk is controlled, then I call T sub lambda of x a risk controlling prediction set. So it's a, it's a set of pixels that controls the false negative rate at some level alpha. Okay, and this delta is a high probability parameter. It usually doesn't matter much. Does anyone have questions here?
I want to finish it, and then I want to come back to the IID part, especially for using some convolutional network to do the classification. I think the classification is per image, not per pixel, but then we need to calculate per pixel. So that's where I'm getting a bit confused. But I think after we finish the explanation, I want to.
Yes, sounds good. Yeah, we can return to that if you want. Okay. So remember, we have this risk here that, this white line is unknown to us, but we want its sublevel set, its alpha sublevel set. It's unknown to us because we don't know the true false negative rate. All we can do is estimate it from our calibration data. So let's do that. What I'll do is I have this loss function. The loss function is 1 minus the fraction of good things. It's that thing that I showed you before. And I take the empirical average of the loss function. Right, so I take 1 over n times sum of loss functions over my calibration data. Okay, I call that r hat. Now I've plotted r hat. It's got some fluctuations because of the fact that n is not infinite. Now let's say I just took the alpha sublevel set of r hat lambda. Is this okay? So that's a question for you guys. Is it okay to take the empirical false negative rate, my estimate, and just threshold it here and say any lambda where my risk is below alpha works. My estimated risk is below alpha.
seems to cross back over in the middle there.
But why does it do that? And is it okay that it does that?
We don't know the distribution of the original images, right? Like we don't know if, for example, it's something to do with if the first images that we've seen were, let's say, without a tumor, or all of them were with a tumor, but then the next ones are without. That's like a completely different alpha.
So let's assume, so the thing that we are assuming here, as with everything in conformal or distribution for uncertainty quantification, so far at least, is that the data is all exchangeable. So you can imagine that it's just like randomly shuffled. So you don't have like these pathological cases except with a very small probability. And that's what the delta is, actually. The delta is the probability that, like, you know, my calibration set, just due to random sampling variation, isn't representative of the next sample.
So in that case, I'd say yes, but I feel that as a trick question, I should be saying no, but I don't see the reason why no. So
yeah, right. So the answer is no. And the reason why it's no is because the n in my calibration data is not infinite. So if n were infinite, by law of large numbers, this would converge to R of lambda, the true risk from above. But because n is finite, we have these fluctuations. So that's why it violates here, for example. And these fluctuations mean that our estimate may not be reliable. So we might include a bad lambda in our set. What's up?
So it is the case that for infinite n, then you shouldn't have this cross back over in the middle thing. Like you should have a continuous
correct,
range
yeah.
below.
Mhm.
Okay, yeah, that's
For infinite n,
sense.
it's just going to look like that smooth U that we had above.
Right.
But n is not infinite, so we need to do something different. We need to account for that, those finite sample fluctuations. So the real procedure that we used to do this is called learn then test. And the idea is pretty simple. It's just like sort of the name says. What you do is you create a null hypothesis for each possible value of lambda, and you test it with the statistical, like you provide a p-value for it. And if it's less than some value, then you accept it, or you reject the null hypothesis. So the way that this works is like, let's just imagine that we took the space of all lambdas down here and we discretized it. Just think about NP Lin space, you know, just finely chop it up. And now what I do is for each lambda, I associate the following null hypothesis. I associate the null hypothesis that the risk is not controlled, that the risk is above alpha, right? So this event is the event that we're interested in. That's the null hypothesis. And if that null hypothesis is rejected, that means the risk is controlled. That means we're in this event. Okay, so that's what we're going to get p-values for. We're going to get p-values for this null hypothesis via a concentration inequality. And then we're going to combine our p-values via multiple testing. So we're going to use like von Ferroni correction to combine our p-values. And then we're just going to get a rejection region down here that controls the family-wise error rate. In other words, we're going to get a rejection region such that everything that we reject, every null hypothesis that we reject, corresponds to a lambda that controls the risk. So that's the high-level idea. All right. So one question might be, how do we get p-values? You know, what does a p-value even mean? So a p-value is like the strength of evidence for or against your null hypothesis. So remember, our null hypothesis is h sub lambda, r of lambda is greater than alpha. And if the p-value is large, that means our data is consistent with this. So when would a p-value be large? It'd be large in this case. Up here, it's pretty clear that our risk is above alpha. Down here, our p-value is going to be small because our empirical risk is very small. And the fluctuations with that n wouldn't allow it to be above that line except with very, very small probability. So that's when your p-value is going to be small. Okay, so this, by the way, is Hoeffding's inequality, and Hoeffding's inequality can give you a p-value that's distribution free. So as long as I have bounded scores or a bounded risk, Hufting will give us a p-value that works no matter what random variables you give me, no matter what the distribution is. So this is a p-value that you can use, and there's stronger p-values that we talk about in our papers. Okay, so that's how I get a p-value for this. But then the question is, once I have a p-value, why can't I just threshold it at level delta? If I want an alpha delta risk controlling prediction set, i.e. that I don't violate my risk except with probability delta, why can't I just take all p-values that are below delta? Does anybody know the answer to this?
Let me think about it 1 second.
Is it again going to be some finite sample thing or something?
Not finite sample. It has nothing to do with n. This holds actually for, let's say, like the more abstract setting is, let's say I give you I give you H1 and H2, which are two null hypotheses. I give you p-values P1 and P2. I want to like reject, I only want to accept a, let me think about this. I only want to reject a null. I only want to reject a null with at most probability delta. So I want probability reject null to be less than delta. Why can't I just threshold these at level delta? P1 and P2.
Then you'll have two of them. Like,
Yeah.
and you'll need to account for how many of them you're taking.
Yeah, that's correct.
Along the right.
That's correct. So, the probability that I falsely reject this guy when I threshold at delta is equal to delta. That's the definition of a p-value. The probability that I falsely reject this guy when I threshold at delta is also delta. That's the definition of p-value. But when you look at both of them together, the probability that I reject at least one falsely is larger than delta, right? Because there's two of them. So I need to correct for that. In fact, if there's big N lambdas in my set, I need to divide this by N. Right? That's called the Bonferroni correction. There's actually less conservative things that you can do. There's ways of doing this that you actually don't need to incorporate that factor if you know certain structure about your loss. But in general, you do stuff like dividing delta by N to correct for this multiplicity. It's called multiplicity correction.
Makes
Okay,
sense.
so great. Yeah, this is the Bonferroni correction that I've written here. You just divide delta by N and test everything at level delta over N. So now we know what our procedure does. Our procedure discretizes lambda. We get p-values for every lambda, and then we use a multiple testing scheme to give us a big set here. So what are the practical implications of this? The practical implications of this is that we can do any prediction problem and control essentially any notion of error that we want. So we can do things like multi-label classification. Multi-label classification, my loss function might be something like the false negative proportion, the FNP, right? It's just like we had before. So I want a classifier that gives me a set of classes such that I contain 90% of the true classes that are in my image. So I don't miss any except with, or I don't miss more than 10% with high probability. Okay, and this is the result here. Let's not worry about the numerical results. Those are a little bit fine-grained. But the nature of the output looks like this. They're prediction sets. And therefore, multi-label problem, where I care about a guarantee on the whole set of labels. It's not just Y is in my set. It's Y is a set, and T is also a set. And I'm caring about their intersection or their containment properties. Do you have a question here?
No, I was just thinking how it connects at the beginning of the talk when we showed the multi-label, figuring out in the head that it makes sense. Yeah.
Okay, sounds good. Yeah, so this is a little bit different in nature from conformal. As you can see, it's technically quite different, but they're united by the fact that they're distribution free, right? They don't care about the distribution of the incoming data. You can also do this for something like hierarchical classification. So I can define all sorts of exotic loss functions. Like, let's say I have a hierarchy. You know, now that we're doing ImageNet, so you can think about this as the WordNet hierarchy. And, you know, there's animal, cat, dog, spaniels, and this is like, you know, English settler spaniel or something. And then this is my Siamese cat or whatever. And so you can define loss functions on the tree. You can say, well, what if my classifier is sure that it's a spaniel, but it's not sure what kind of spaniel it is? Well, then I can make my tree predict at the right resolution such that in graph distance, it's not too far away from the true label. So the way this would work is my loss function would be, well, my sequence of nested sets, my T function would be some interior node here. And the interior node is just indexed by set of leaf nodes, right? It's the lowest level on the tree such that these three labels are contained. And then my graph distance would be, well, how far away is spaniel from any ancestor of Siamese cat? So let's say I predict spaniel, but the answer is really Siamese cat. Then this loss would be like 2 in graph distance. And I can guarantee you that you're not going to be more than 2 away or not more than 1 away in graph distance. And in that way, I get hierarchical predictions. My predictions will look something like this. So the true answer is fire screen. The model thought it was window screen. That's the top 1 class. And then with the hierarchical prediction, we chose screen. And it's true that this fire screen is a window screen. Fire screen is a screen. It's not true that it's a window screen. So now my model is predicting at the right level of resolution for how confident it is. This is also true. So my model thought this was a candle. It's really a table lamp. And an ancestor of both of these is apparently lamp. Well, apparently a candle is a type of lamp in WordNet. And so this was also at the right level of resolution. Same thing was true here. My model thought it was candle. It was actually spotlight, which I guess is their word for lava lamp. Actually, the label was wrong here, right? This is a lava lamp, not a spotlight. But in any case, the model got it correct because it said lamp when we predicted at the right level of confidence. And here, this is the example that I've shown on the right. My model thought it was a hot pot. It's actually a consomme, I guess that's how you say it. Our prediction was dish. So the right resolution of prediction was this dish class. And by doing this properly, we controlled graph distance. All right, we used exactly the same set of techniques. So our lambda was how far up the tree we go. Our risk function was graph distance.
All right, I think I missed this. How do you decide what level to predict at? Like what the
way you decide what level to predict at
is?
Yeah, don't worry. I think I'm going through this a bit fast. So just so you get a perfect understanding of this, I'll explain it in detail. The way that it works is that I take my model, my ImageNet classifier, and for each leaf in WordNet, I have a mass, right? That's like the softmax score. Okay. And now what I do is I index this function t. T sub x is indexed by lambda. And lambda is just going to be like the amount of softmax mass that I include in my prediction set when starting from the maximum likelihood prediction. So I start at this node, which is, settler spaniel or whatever. And that's because it has 50% of the softmax. So my softmax score there is 0.5. And then I just go up the tree until I hit the spaniel node. And then I contain 70% of my mass. And then I stop. Okay? Now, because everything has a common parent, I don't actually need to report the whole tree. I can just report the name of this node. That's the resolution of the prediction that I'm reporting. And now the whole game is how I pick lambda.
Exactly.
Yeah. And I pick lambda by, constructing my risk function as a function of lambda. So in this case, it's monotone, right? Because the higher up I go, the more I'm likely to contain my true answer. And then I just pick, the lambda that's furthest to the left in the set that I've identified lambda hat via my multiple testing scheme. So we run learn then test and pick the leftmost lambda.
Wait, sorry, what is the leftmost here?
Do you see this plot that I'm drawing?
Yeah.
So this is a risk function. This is like our hat of lambda that I've drawn.
Yeah.
And then we pick, and this lambda hat here is the set we identified with learn then test. It's this thing.
Right.
And the leftmost lambda is just the one that's furthest left on the x-axis.
Oh, sorry, I didn't realize the range for lambda hat there. But yeah, that makes sense. So you pick
So this would be lambda
point
hat.
where the risk is. Yeah, makes sense.
Yeah, and this would be, you'd identify this lambda hat by finding the leftmost p-value that's below your Bonferroni correction or something. Actually, there's a less conservative way to do it, but yeah. In this case, you actually don't need to pay a Bonferroni penalty, interestingly enough. You can read about that in the gentle intro. It's a better multiple testing schemes will give you better lambdas. Now, I'm not going to go into this in too much detail, but you can also do this with multiple dimensions of lambda. So what if I don't have just one threshold? What if I have, 3 thresholds? In this case, if I'm doing like instance segmentation, I have something that tells me how many objects I have in my image. So, this would be the function O hat of X. That's saying how many objects. And then for each object that I have, I get a softmax, a vector of softmax scores, right? And from those, I want to give you prediction sets that contain the true class. So there, I want to give you coverage. And then also for each object, I get mask activations. And I want to give you an object mask that has good IOU with the true mask. What if I want to control all that stuff together and give you a guarantee that, like, recall greater than or equal to 1 minus alpha 1, IOU greater than or equal to minus alpha 2, and then coverage greater than or equal to 1 minus alpha 3. The fact is, you can do this too. So the technique is general enough that by calculating all 3 of your risks at each point in this sort of volume of thresholds, so you have lambda 1, lambda 2, lambda 3. For each point in here, you have 3 risk functions: R1 lambda, R2 of lambda, and R3 of lambda, where lambda is a vector as well.
So is leftmost here the smallest norm or something? Some analog?
Well, that's a good question. It's not always clear that you want any extreme point here. So for example, with IOU, you might want the thing that has, you might want to find the point that has like sort of the most extreme recall and the most extreme miscoverage. But within those, you want to find the point that maximizes your IOU. So you might want to actually do a maximization problem over your thresholds in addition to controlling 2 things tightly. So you might not want the leftmost. In the IOU case, you might want this value because that gives you the best IOU. You might not want to violate. This might be more like a constrained optimization problem. And you can do that as well. But it's sort of problem dependent which threshold you pick out of the thresholds that you know are valid. So in any case, you can do this. It's not too different from what we did before. All you do is you associate a p-value to each of these things. You have a vector of this is your null hypothesis is that this vector is greater than alpha 1, alpha 2, alpha 3. And if that null hypothesis is rejected, then all 3 risks are controlled. And then you do multiple testing on it to try and identify the whole volume of thresholds that work. And then you pick a point from within those with whatever method you want. And this is the result. This is with Detectron 2, by the way, that you take the input image and then you run this algorithm and you get prediction sets for every object. All the things are highlighted with, a bound on the IOU. And a lot of the objects are highlighted. So you have a guaranteed that you're going to identify at least 90% of the objects in the image or something. Actually, I think in this case, it's 50%. Okay. So that's basically the end of the talk. The thing I want to highlight here is that this technique is so general that it can handle almost any problem that you throw at it. So if you can get any statistical error rate. If you want to do out of distribution detection plus guarantees, if you want to do selective classification or selective regression, if you want to say my MSE is controlled subject to the fact that I decide to predict, you can do that. It's sort of a big playground. Anytime that you want your model to sort of certify some rigorous notion of reliability, that should be possible using this set of techniques. So we have a couple minutes for questions. Feel free to ask.
Yeah, I want to understand again the IID part. Like when we're mixing the pixels. So the model is trained, let's say it's some sort of convolution model, usually, right? But then because we want to be randomly sampling the pixels without any dependence between them, we got to shuffle the pixels themselves. But then how can we combine it with the score that the model gives per pixel? I'm missing something there. Maybe
let's just zoom out for a second. In practice, we're not shuffling the pixels. That was just sort of an example that I brought up. In practice, what we're doing is we have the following. We have a data set of calibration points, xi, yi, where this is an image of tumor, and this is the binary mask, true tumor pixels, R +1. And each of these points is drawn exchangeably. So we assume that the images are exchangeable. And then the guarantee that we get is that the probability that like F and R, which is a property of the way T of X intersects with Y. It's a property of, expected loss of T of X and Y, where the loss is that 1 minus the good things that you contain. Where this probability is over this whole thing. So you're not even operating on the pixel level here. Now, the way that it interacts with the pixel level is, how do I produce T of X? Well, T of X is going to be equal to the set of all I comma j, such that my model's prediction, F hat X, I, j, is greater than lambda. But this is sort of like, this is at the resolution of Y, not at the resolution of a pixel. It's a set of pixels. Is this making sense?
I gotta think through it 1 second. Let's see. 1 second. I need to look back at the formula in the beginning. I think it'll make sense once I look back at it.
Where are we looking?
Let me look also.
Like here?
One of the first slides. No, one of the really first slides when we were talking about the IID importance.
Oh, very first slides?
Yeah.
Like here?
Yeah, it makes sense. I understand. Yeah. Okay.
Great. Any further questions?
It's super cool.
Thank you.
Yeah, for sure. This was a very engaging talk, Anastasis. It's late here, but I don't feel tired, so that's the best indication of an engaging lecture.
Thanks so much. It's very sweet.
Yeah.
Yeah, I guess it's 8:30 for you now, right?
Yeah, almost nice. Yeah, 9:30, I think. What time is it? 9:30. Anybody else questions on the YouTube? I didn't see any, so nothing from there.
I'm good, thank you. Thank you both for putting this together.
Yeah,
For
my
sure.
pleasure. Thanks for being here.
Thanks so much.
For sure. Anastasia, if you have any closing remarks, that's the time. Otherwise, I'll wrap it up for us.
No, I don't have any closing remarks. I think I said everything I needed to say. Happy to, if anybody wants to reach out and ask further questions, my email is always open.
I'll take this chance to say again, really thank you for the talk. Go ahead. How do you spell your name? Sachit, is it, or Sachit?
It's such it.
That's it. Okay.
Like the word such and it, you just smash them together.
So if you have you raised your hand before, you have a question?
No, I was just waving by. But
Sure.
yeah. Thanks for the talk and thanks for organizing.
Yeah, thanks everybody for joining. Those who will be watching the recording, hope you find it as engaging as we did. Anastasis, again, really thank you for this great talk. Was very interesting.
My pleasure.
And everybody have a good evening, good day, good morning, wherever you are. And bye for now.
Okay, guys.
Thank you. Thank you.